Great, thanks a lot for the wonderful introduction. So I'm going to give a tutorial on machine learning for economics and finance and TensorFlow 2. I'm a senior economist in the research division of the Swedish Central Bank. I mostly do work on computational economics, machine learning, and I'm now doing work on quantum computing. In addition to this, I also teach courses for the DataCamp platform, so relevant to this presentation. I teach their introduction to TensorFlow and Python. And I also recently published a book entitled Machine Learning for Economics and Finance in TensorFlow 2. And we'll draw from that book during parts of this presentation. We will have a separate Q&A session at the end. And so I'll take any questions. So I'll collect questions during the presentation and then answer them afterwards, just so you know. Okay, so to give an overview of the tutorial, we'll split it into 3 different parts. So the first part is a 60-minute lecture. Then we'll have a 15-minute live coding tutorial, and then we'll end with a 15-minute Q&A session. The lecture itself will be split into 4 parts. So we'll start off by introducing TensorFlow and motivating its use in economics and finance projects. Then we'll cover 2 related sections, one on structured data and one on unstructured data. Now in economics and finance, we have many tabular data sets that can be used as is without feature extraction. So we can, of course, try to improve by extracting features from the tabular data, but that's actually not a necessary step as it is in, say, image processing or natural language processing. So we'll start off by taking the data as we typically use it in economics and finance, and we'll use a less familiar set of models. So we'll make use of neural networks and gradient boosting and so forth, instead of the standard linear models, which are used more commonly. We'll then augment the structured data with unstructured data. So specifically, we'll show how we can extract features from text and then use them in machine learning models alongside our more familiar tabular data sets. And then we'll have a self-contained section that looks at generative adversarial networks, which have recently gained some use in economics and finance. So we'll see 2 applications, one related to simulation and one related to estimation. I'll say the first two sections will contain a little bit of code, and then the second 2 sections will be more conceptual. But in the live coding exercises, we'll do exercises related to the 3rd and 4th sections. Okay, so we'll start off with a broad overview, broad introduction to TensorFlow, and what it is that TensorFlow can provide as a machine learning library for economics and finance. Now, what is TensorFlow? It's an open source framework for machine learning that was introduced by Google's Brain team in 2015. One of the benefits of using TensorFlow is that it has a large community. It has tools that can be used in production settings, and it has deep capacity for distributed training. So for instance, if we have a problem that we need to train on large amounts of data and we want to do distributed training, so we want to either distribute across, say, multiple GPUs within the same device, or we want to distribute it across multiple devices in a network, we can do that with essentially a couple lines of code in TensorFlow, and we don't actually have to change, how we define our models. Now, TensorFlow was constructed with the intention of being used for neural networks, and so in that sense, it's less of a general machine learning framework than, say, scikit-learn, which can be used for many different types of machine learning problems. But actually, the tools that you use to construct and train neural networks can be used for any graph-based model. And in fact, many models used in economics and finance can be formulated as a graph-based model and therefore can be solved in TensorFlow. So tree-based models, for instance, we have capacity in TensorFlow in 2 different libraries. So in the standard TensorFlow distribution, we have the estimators library, which we can use for tree-based models. And we also have an extension of TensorFlow that can be used to solve tree-based models. And then we can also reformulate many theoretical models in economics and finance as a graph-based model and solve them in TensorFlow. And we'll see in a couple of slides why it might be advantageous to do that. We can also do this with reinforcement learning. So if we want to construct, say, a high-frequency trading system, or we want to say on the supervisory tech side, divide a reinforcement learning-based system to detect money laundering and transactions data. This is something that we could develop making use of TensorFlow. Now, I mentioned earlier that TensorFlow has a large community. So this is the number of GitHub stars by machine learning framework. You can see that TensorFlow, since it was introduced, has been one of the most popular machine learning frameworks. Now, this data ends right before 2020. And I think if we look at the last year and a half, we'll probably see that PyTorch, starts to catch up, and Keras as a standalone framework starts to catch up. But nevertheless, TensorFlow benefits from a large community and as a consequence of a lot of additional code that's put together by the open source community. Now, how can we use TensorFlow in economics and finance? One way in which we can do this is in causal inference problems. So very often we're interested in economics and finance and establishing causality. And we sometimes do this using instrumental variables regression. Well, the first stage of an IV regression is a prediction problem. And we could, in general, do prediction better with machine learning models than with the linear models that we use in economics and finance. And so we've since very recently seen the development of a number of hybrid machine learning econometric methods that can be used for causal inference purposes. We can use TensorFlow and machine learning more generally to do feature extraction. So we can take, for instance, transformer models, and we can use them to extract text features, and then we can use those text features, in a text regression or some other model to augment the tabular data that we're otherwise using. We could do nonlinear modeling, so we can move away from traditional economic and financial models to make use of the models that are more common in machine learning. We could do simulation exercises with TensorFlow, so we can train a generative adversarial network, and then we can use it to conduct a Monte Carlo experiment. We can do dimensionality reduction by training an autoencoder and making use of a latent state. We can do reinforcement learning, as we've discussed. And we can also do a number of research-related tasks that would be difficult to do in machine learning frameworks that are structured at a higher level. So for instance, if we want to look at model uncertainty that arises from the fact that we have a random initialization of our, say, parameters in a neural network, or that our training process is stochastic, we can actually use TensorFlow probability to examine the uncertainty that's generated in terms of the predictions. Okay, so to be a bit more concrete about what it is that we can do with TensorFlow, in TensorFlow 2, we see a reorientation of the library around higher level submodules. So if you use TensorFlow 1, you probably remember working with static graphs and doing defining and training models at a very low level. But there's now the option to use higher level submodules, and if desired, mix those with lower level operations. So you really get the best of both worlds in the sense that you can define models and train them with a small number of lines of code, but you can also do far more advanced things if you want to do research applications and so forth, where you need to modify standard architectures. That's also possible. So two of those high-level submodules that we'll talk about are TF-Keras and TF-Estimator. TF-Keras is a high-level submodule for constructing and training neural networks. And we could do the construction and the definition of models essentially at 3 different levels. So we can define a sequential model where we just instantiate an empty model and then append a number of layers to the model and then compile and train it. So this requires very few lines of code and essentially no customization other than the choice of the network architecture. Or we can do things that are more advanced. So for instance, we can use a functional model which allows us to do things like have multiple inputs or multiple outputs. So to give an example, I'm working on a project where we have features that need to enter linearly, and then we also have features that need to enter through a deep neural network. And so with TensorFlow, with TF-Keras, we could very easily use a functional model to create a multi-input model where the features that should enter linearly are isolated in a wide network, and the features that should be allowed to have nonlinear relationships with each other in the target can be isolated in a deep network that allows for nonlinearities. So the functional model, we're still using layers that are that in some sense are fixed, and we set the the number of nodes and so forth in the layer. And then we also have the option to go a little bit further by actually customizing the layers using subclassing. So with TF-Keras, we can go very shallow, and we can define a neural network using a few lines of code. We can go very deep to the point where we're subclassing and we're actually creating custom layers to include in our network. Now, one point of confusion that I've encountered with TensorFlow users is, what exactly is TF-Keras? Because Keras is a standalone, it's also a standalone module which existed, prior to TensorFlow 2. And the answer is that TF-Keras actually has a number of TensorFlow-specific enhancements, mostly related to distributed training. So it might be a little bit confusing, but they actually are separate libraries, even though they share, much of the same core functionality. But then we have the TF-Estimator submodule, and this allows us to define models by selecting a small number of parameters. So this is a very restricted framework relative to TF-Keras, and this is intentionally so. So the purpose of this framework is to prevent common errors that arise in the definition and training process. And so what we do is, use a restricted framework where we're very unlikely to encounter errors, when we serve something, in production. So with TF-Estimator, you're really thinking about developing models for use in apps and other web-based services. Additionally, TF-Estimator has the option to create tree-based models, specifically gradient-boosted trees. You can create either classifiers or regression models. And this might actually be something it's not obvious how to do it in TensorFlow otherwise without coding it up yourself. Now, if you use TensorFlow 1 and you have bad memories about debugging static graphs and working with opaque code, here's a quick comparison of how things have changed between TensorFlow 1 and TensorFlow 2. Whenever you define an object in TensorFlow, it's going to be either a constant or a variable. A constant is something that we won't optimize over during the training loop, and a variable is something we will optimize over. So for instance, your data is a constant, or it can be defined as a constant, and so the weights in a neural network would be defined as a variable. Now, let's say we want to just define a constant that has the value 1, and then we want to print out the value of the constant. Now, in TensorFlow 1, if we do that, we define a TF constant object with a value 1. And then if we try to print it out, we can see that we get this tensor object, which says that it's a constant tensor. We get the shape of the object. We can also see the data type of the object, but we don't actually see the value. And the reason for this is that all we've actually defined here is an operation to define the constant. We actually have to execute that operation in the context of a session in order to actually generate the constant itself. So here we create a session, and then we evaluate that operation and print it out, and we get 1. Now, if we want to do this in TensorFlow 2, we just define a TF constant, we print it, and we get a TF tensor object with a shape and a data type, but also with a value. Now here you can see the value is contained in the attribute NumPy. Now, this might also be confusing, just like, what are we doing with Keras? Isn't TensorFlow a backend for Keras? Here, why is NumPy, another module, a parameter of a tensor? And the reason for this is that if we use the NumPy attribute, we can actually recover a NumPy array that corresponds to the value in this constant term. So we can convert it from a TensorFlow object to a NumPy array. Okay, so what if you still want to use static graphs? So you want the performance enhancements that come from compiling your code. So let's say you have a function which takes a set of features X and a set of variables. These are trained parameters beta. And then it makes a prediction for each of those. It makes a prediction for each observation. Now, if you want to compile this, all you have to do is use the decorator @tf function. And this will not only compile the function, but it will compile any functions that are called within it recursively. So there's a very simple functionality for using static graphs. Now, you may also remember that at the end of TensorFlow 1, something called eager execution was released, and this allowed us to execute all of our commands iteratively, like we did on the previous slide for TensorFlow 2. What's happened in TensorFlow 2 is that that's now enabled by default. So we actually have to use this TF function decorator if we want to create a static graph and compile our code. Okay, let's step back a little bit and talk about what a tensor is, because in TensorFlow we're defining tensors and then we're applying operations to them, which are also tensors. So everything we're working with is a tensor. Now, if you have a background in physics or you are familiar with linear algebra, you might have a specific idea in mind for what the term rank means and what the term tensor means. And it's actually, for the most part, going to be a little bit different from what they mean in the context of TensorFlow specifically. So whenever we use the term tensor, we're just talking about a multi-dimensional array that's rectangular, nothing else. And whenever we talk about rank, we're talking about the number of dimensions that multi-dimensional array has. So a rank 0 tensor, also called a scalar, is just a number. A rank 1 tensor, which could be a row or column tensor, is a vector. So it just consists of a number of scalars arranged in a row or a column. Now, if we have both rows and columns, then we have a rank 2 tensor or a matrix. And then if we have multiple matrices with the same number of rows and columns, and this forms a rank 3 tensor or a 3 tensor, and we can continue from there. For the most part, we're not typically going to use anything much higher than a 4 tensor, at least when it comes to training neural networks. But we can continue to extend this concept up to K tensors in general, which have K dimensions. Okay, so how do we actually define tensors in TensorFlow, and how do we perform operations on them? As I mentioned earlier, everything that we work with is either going to be some form of constant, so it might not be called a constant object, but it's something that's not trainable, or a variable which can be trained inside of the training. So let's start by defining a scalar, so a 0 tensor. We'll do this by using TF constant, and then as the first argument, we supply its value, and then we want to supply its data type. So if you're not careful in defining data types in TensorFlow, you can encounter situations where you're, say, multiplying 2 variables which have different levels of precision, which is going to throw an error. So you actually want to be careful in choosing data types for your variables and defining them. Now, let's say we want a trainable variable. So let's say we're defining weights in a neural network. We could do this by using TF variable and then passing to it the matrix that we want to define, and then setting its data type. Now, if we want to do a random initialization, one way in which we can do this is to start by generating a tensor randomly by, say, drawing from a normal distribution. So this is something typically we do whenever we initialize parameter values in a neural network. But that tensor object that we've just generated using TF random normal is actually going to be a type of constant object that won't be updated in the training loop when we're performing optimization. So we actually need to pass that to a TF variable once we've defined it, if the objective is to do initialization. Now, how about performing operations on these tensors that we've defined? We could do this using, so we can do this, I'm leaving out many operations here, but I'll talk about just some simple ones and what are the important things to understand about them. So we'll look at addition, multiplication, and matrix multiplication. And with just addition and matrix multiplication, we could already do almost everything when it comes to, say, defining, a neural network with just dense layers outside of the activation. So here, if we want to add, say, a scalar and a tensor together, we could just use the TF add operation. And if we want to, say, add two tensors together or two matrices together, what we have to be mindful of is that the two tensors that we're using have to conform to the operation that we're performing. So if we're performing addition, they have to have the same dimension unless we're broadcasting. So unless we're taking, say, a vector that has the same number of rows and columns and adding it to all of the rows and columns in a given tensor, or we're doing the same thing with a scalar. If we're not broadcasting, then it has to be the case that our tensors have the same dimension in order for us to put them together. And with matrix multiplication, again, in order to have two conforming matrices, it must be the case that the number of columns of the first matrix is equal to the number of rows in the second matrix. So the first thing we check is, are the dimensions of these conforming? The second thing we want to be mindful of is whether the tensors that we're using are multi-dimensional, are NumPy arrays, or whether they're TF constants. So we can actually use NumPy arrays directly in TensorFlow, but if we perform an operation between two NumPy arrays, and we don't use this cumbersome operation of TF-add or TF multiply, but instead just use the addition symbol or the multiplication symbol, then that operation will actually happen in NumPy rather than TensorFlow. So if you want to use just the plus symbol or just the multiplication symbol, you can do that, but you want to make sure that at least one of the objects, one of the tensors involved is a TF constant object or some type of TensorFlow object, and that they're not both NumPy objects. Otherwise, you need to actually explicitly use TF-add. Okay, there's one additional thing that I'm going to say about the value of using TensorFlow in economics and finance problems, and that is the value of being able to use automatic differentiation. So, and when we train neural networks, we very often have complicated function compositions, and we need to compute derivatives. So let's say we have some function g that's composed of the function f, and we want to compute the derivative of g with respect to x. That's what TensorFlow is designed to do well. It's to do that using something called automatic differentiation. Whereas in economics and finance, we typically either do that symbolically or we do it numerically. And there are some substantial benefits to doing automatic differentiation, which we'll talk about quickly. So let's look at an example where g is 3 times y and f of x is x squared. And we're, say, performing an optimization problem, and we're at x equals 2, and we need to compute the derivative of g with respect to x evaluated at x equals 2. Now, if we use symbolic differentiation, we can simplify g of f of x by just writing it as 3x squared. And we know how to take the derivative of that, so that gives us 6x. Then we can just evaluate that at x equals 2, and we get 12. Now, if we wanted to do this numerically, we'd have to use an approximation. So we could use, say, the forward difference method. So here what we do is we take x and we'd add some small amount to it, h, and we'd evaluate g of f of x at that point. And then we'd also evaluate g of f of x at x, take the difference and then divide by h. Now, as h goes to 0, derivative of G with respect to X converges to its true value. We can actually express this analytically by just simplifying this expression to 6x plus h. So h is going to be the size of the error that's introduced by using a numerical approximation. And so if we evaluate that at x, we get 12 plus h, where h is the size of our error. Now, computing derivatives symbolically is a problem. Even if we use high quality symbolic differentiation libraries, we can get very inefficient and complicated expressions for derivatives. And if we do it numerically, numerical derivatives are going to contain some error, and they may actually be very sensitive to the size of the finite difference that we choose. So they're going to be both unstable and contain error. Now, if we use TensorFlow, we'll use by default automatic differentiation, so without even thinking about it. How autodiff differs from numerical and symbolic approaches is that we start by decomposing the derivative symbolically. So we use, in this case, the chain rule to decompose it into two partial derivatives. And then what we could do, we can write down those derivatives. So partial of G with respect to Y is 3, and partial of F with respect to X is 2X. Then we can sweep through this chain of derivatives going in one direction or the other. So we can start with the partial derivative of F with respect to X, and then we can evaluate that at 2, and we get 4. And we do the same thing with the partial derivative of G with respect to Y, which is already constant, so it's just 3. And then we can take all of these partial derivatives that we can computed, and we can multiply them together, which gives us 12 in this case. So auto differentiation, we're solving for the each partial derivative as an exact numerical value, but we're solving for the partial derivatives themselves symbolically. So it's a combination of the two approaches that doesn't introduce error and makes it tractable to compute the derivative of, when we have many nested functions, which is common with the case. Okay, now let's move on to a section on structured data, where we're going to look at the use of tabular data, but with machine learning models. So we use the data that we normally use in economics, but we use models that we typically don't use in economics. Now, one of the benefits of one of the advantages that we have in economics is that we have many tabular data sets. So, for instance, the St. Louis Federal Reserve's Fred system has something like 1 million publicly available time series, which can be used in macro and financial models. And so we don't have the same problem that we have in image processing and natural language processing where you can't do anything at all until you've extracted features. We already have lots of high quality features. Now that's one point of departure with standard machine learning or problems in the machine learning domain and problems in economics is that we already have a lot of high quality features that we can use as is. We can try to improve on them with feature extraction, but we don't have to as a first step. The second difference is that we typically use linear parsimonious models that are guided by theory in economics and finance. So we want to do causal inference, we want to do hypothesis testing, and we want to be able to interpret the results that we get. So the direction that we've gone empirically is very different from the direction that the machine learning literature has gone in, with the exception of forecasting tasks in economics and finance, where there's a lot of overlap. We do also have use of penalized regression in economics that goes back a long time, but that's not surprising in some sense because it's a linear model. Whereas tree-based models and neural networks are only starting to gain widespread use. So in this section, we'll concentrate on an example where we forecast consumer price inflation. And so we're going to build off of one of the very first neural network forecasting applications in economics in a paper by Nakamura in 2005, which just made a simple attempt to forecast inflation using essentially an autoregressive model in a dense neural network. Now, the type of data that we'll use is tabular data, so it'll be time series data. We have observations on inflation, unemployment, hours, earnings, and on the M1 component of the money stock. Inflation, hours, earnings, and M1 are going to be in percentage differences month over month, and unemployment will be in first differences. Now we'll step through a very minimal example in which we don't use best practices, so we're not going to bother to use a validation sample or a test sample. We're not going to check for overfitting and so forth. The purpose is just to show how to set up the model, how to set up a model that we could use for this forecasting task, and then also how to make use of models that are specifically designed for the purposes of sequence processing in TensorFlow. Okay, so we start off by importing a number of modules on NumPy and Panda and TensorFlow. And then we're also going to import from TensorFlow Kera's preprocessing sequence time series generator, which will allow us to create generator objects that handle the creation of time series and batches. So I'll talk a little bit more about that on the next slide about what that entails. But it will save us a lot of work on the data preparation end to just to instantiate a generator that does this work for us. So we start by importing the data in pandas. Then we're going to select only the inflation column. So we'll start off with just a model where we use a lag of inflation. We'll convert this to a NumPy array called inflation. Then what we do is, since we're using an autoregressive model where we use lags of inflation and no other features, we're going to pass inflation as the first argument, which is the set of features, and inflation as the second argument, which is the target to time series generator. Then we'll also pass a length, which tells us how many lags we want to generate, and also a batch size. So how many examples do we want in each batch? And then we'll call this generator object gen. Now, what is this actually doing? Well, it's taking the lag values and it's mapping them to a feature set, and it's drawing 12 of these for each of the batches in the training process. Now what we're going to do is define a TF-Keras sequential model. Now I'm intentionally writing out TF-Keras model, sequential, and so forth, instead of just importing the sequential model directly, just to reinforce where things are coming from and so forth. Of course, you may want to import layers and so forth directly so that you can keep your code a little bit cleaner and more readable. In any case, we're going to use the simplest type of model. We said we could use sequential model, functional model, or custom layers with subclassing. We'll just instantiate a sequential model. Now we have an empty model, which we can append layers to. So the first thing we'll append to it is an input layer, and we have to specify a shape of the input. So we know we have a time series model, which contains 4 lags as features, so the shape should be 4. Then we're going to add a dense layer with 2 nodes and a ReLU activation. So this is our one hidden layer in the model. And then we'll specify an output layer, which has a linear activation because we don't want to restrict the range of predictions. We're predicting inflation. We're not doing a classification task where we want to return probability. Now, once we specify the model architecture, the TF-Keras, we now need to compile the model by specifying at least a loss function, so it's mean squared error in this case, and an optimizer, the adaptive moment optimizer. Then we can optionally print out a summary of the model architecture. And this is quite useful because it will help us to see how heavily parameterized the model is. So here we can see that the model has in total 13 parameters, all of which are trainable. Now in the first hidden layer, we have 10 parameters. This is because we have 4 inputs and we have 2 nodes in the hidden layer. And so the amount of weights that we're going to need is going to be 4 times 2 is 8. And then we have 1 bias for each of those nodes, so that gives us 10 parameters in the first hidden layer. And then in the output layer, we're going from a hidden layer that has 2 nodes to an output layer with a single node. So we're going to need 2 weights, and we're also going to need a bias again. So that adds 3 additional parameters to the model. Now, when we're ready to train the model, we can use fit generator and pass our generator to it. So the generator will generate these samples from the data that we provided and the generator parameters that we set. It will do this for 100 epochs. So the epoch will be a full pass over all of the mini batches of our sample. Now, if we want to see how well this model predicts, we can use predict or predict generator, which is a method of the model. And then we can predict the values for the time series using the lags of inflation. So here we see the true values in blue and the predicted values in orange. Now, as I mentioned before, we haven't separated this into test and training samples. We haven't done validation. In fact, if we do that, we can see that actually the model is overfitting a little bit, and that partially explains the good fit that we see in the data. But to save time, we'll skip those tasks. Now, using a dense model for time series is inefficient in many instances. So we need many more. So we need to use many parameters because we're treating each of the input values as different, and we're not making use of sequential information. Now, if one way in which we can reduce the size reduce the number of parameters in the model is to make use of a sequential model, which explicitly makes use of the fact that we have data in a sequence. So we can actually explicitly make use of the time dimension to reduce the number of parameters that the model needs. So here we have our set of inputs. And then instead of passing them to a dense layer where we multiply them by weights and we add a bias and apply an activation function, we instead pass them to cells which do sequential processing. So essentially we pass each of the observations to the cell in sequence. We update a hidden state, we pass it to the next value in the sequence and so forth until we get to the output state. Now, typically we handle sequential models using recurrent neural networks, although we don't usually use recurrent neural networks exactly because they have two problems on the training side. One is the vanishing gradient problem, which makes it hard to train the model for large sequences. And the second problem is they don't do a good job of representing information that's far apart in the sequence, but is valuable, but has predictive content. Instead, without explaining in detail, we're typically going to use models that use some sort of gating mechanism, like the long short-term memory model. Now, if we want to modify our model to use an LSTM model, which is a type of recurrent model, and we want to use LSTM cells rather than standard nodes in a neural network and a dense neural network, we could just change dense to LSTM. We can set some number of cells, keep everything else the same, and now we have a model that processes sequences. Now let's move on to tree-based models as an alternative to neural networks. So tree-based models perform a sequential partitioning of the data. So we start off at the root of the tree with our full data set, and then we sequentially move through internal nodes and branches until we've exhaustively partitioned the data set into subsets that say make a classification or make a prediction about a specific continuous value. Now, tree-based models achieve state-of-the-art forecasting performance on tabular data, and gradient-boosted trees seem to perform particularly well, so often better than random forests, and certainly much better than just standalone decision trees. And we have two different implementations of tree-based models in TensorFlow. So we have gradient-boosted trees in TF Estimator, and also the TensorFlow Decision Forest extension, so the TFDF extension. So you can use either one of those to construct and train tree-based models. I won't say too much about the details of tree-based models, but this is a diagram to show you a tree-based model for loan originations. So you start off at the root node, and then you apply a threshold condition, which checks whether an applicant in the sample who applied for a loan had an income that was less than $49,500. If it was, then the tree model says, reject the application. It was just a model trained on, on this loan origination data. Otherwise, we go to another internal node in which we apply another threshold. We have branches where we move, where we again the threshold is either satisfied or it's not. We move, to another set of internal nodes and so forth until we make it to a leaf, where a leaf is, reject or accept output. Now with gradient boosted trees, I should specify this is just a single tree. With gradient boosted trees, what we're going to do is actually sequentially construct the model. So what we do is we start off with one tree and we train that tree to predict some outcome variable y. And then we store that tree in a predictive function g, which we iteratively construct over time. So initially, g is nothing. We train our first tree. That tree predicts y. And then that first tree goes into this predictive function, which is not updated over time. And we train our next tree to try to explain the residual that's left over where we take our target variable and subtract them at the predictive function up to that point. Then we iteratively update, our predictive function after each step. So gradient boosted trees are trained sequentially. This actually limits our ability to do parallelism relative to, say, random forests, which can actually be trained in parallel because each tree is independent of the other trees. Okay, now how can we use gradient boosted trees in TensorFlow? Well, we'll look at the TF estimator implementation. So the first thing that we need to do is define feature columns, which will be containers for the different features in our model. So we use TF feature column, and then we specify the type of column or the type of feature that we're using. So in this case, we're going to have both inflation and unemployment as features in our model, and we'll specify them as numeric features because these are just going to be continuously valued variables. So these won't be discrete or categorical variables. They'll take on real values. Then the next thing that we do is we define the length of our data set, and then we're going to define an input function that generates our training data. So first we take the macro data that we imported, which contains the inflation and unemployment variables, and we're going to take a subset of that data that starts off with the first observation, but only goes to the second to last observation. This is so that we can create features that are lagged. So when we create the target variable, we're instead going to go from the second observation to the last observation. So with our features, we take the lag values, and then what we're going to do is construct a dictionary where the value for inflation corresponds to the inflation column in the training set, and and where unemployment corresponds to the unemployment feature in the training set. And then we define labels, or here in this case, we actually have a continuous target and not labels. We'll then define a list of our features. So this is actually a list of these feature columns. Then what we can do is instantiate the model. So we'll use TF estimator boosted trees regressor. So regressor we use when we want to make continuous predictions. We also have the option to use a classifier for different problems in TensorFlow. Then we'll specify our feature list, and we can then train the model using the train method. TF estimator models also come with other methods like evaluate, which we can use to see different metrics for the model that we just trained. Okay, so I'm going to stop there with the structured data section and move on to concentration on augmenting these models with additional unstructured features from text data. And this can be quite advantageous in the sense that, we have these high quality features, in economics and finance that come from essentially large amounts of publicly available tabular data. But we have these, we also have lots of text that we can make use of to construct features that have never been previously explored and could provide explanatory, a power that we haven't had access to using, more familiar sources of data. So text data is underexploited in economics and finance. We can use newspaper articles, social media content, central bank announcements, earning calls, financial filings. One difference between text data and data in tabular format is that it's unstructured, and we have to convert it to some sort of numerical format before we can include it in a model. So we have to take our raw text, our corpus of text that we assemble, and then we need to find a numerical array or a sequence of vectors or some way in which we code the data before we can make use of it in a machine learning model. Now, if you're interested in seeing an overview of how text has been used in economics, there's a nice paper entitled Text is Data by Jenstow et al. In the Journal of Economic Literature. And this doesn't focus on deep learning, but it provides a nice overview of a number of different econometric and natural language processing issues related to problems in economics specifically. Now, what is the document corpus that we're going to use? I mean, if we have a problem that's a time series problem, so then we want to identify some form of text data that has a time dimension. So say timestamp newspaper articles or timestamp central bank speeches. What are the features that we want to extract from that text? Well, there are a lot of different options that we can make use of. We're going to extract some type of linguistic token, but we have many options available. So to give just a few of these that have been used regularly in economics, we have very simple things like word counts. So we can just take all of our documents, identify, say, the 1,000 most frequently used words, and then count their appearance in each of the documents in the corpus. We can do sentiment analysis using simple methods like dictionary-based methods, or we could do it in a more, using a supervised learning approach. We could do it, say, with zero-shot learning, making use of transformer models like BERT. We have other commonly used text features like the Economic Policy Uncertainty Index, which is essentially a dictionary-based method, but one that is proven to have a lot of value. So this one's been human verified in a number of different studies where we have, ratings of content and text by the EPU index using the dictionary-based method, and then it's compared to human rankings, and it actually seems to perform reasonably well. We can also, say, apply a topic model to a text, extract topic proportions, and then include those as features in a text progression. We can compute entropy over, say, topic proportions to see the extent to which, a conversation in newspapers about a given economic topic is narrow or broad. How orderly or disorderly is it? And capture that with entropy. We have memory, which is a feature that I introduced with some co-authors in a publication earlier this year. So here we make use of the dynamic embedded topic model, and then we construct a specialized feature making use of the dynamic embeddings to measure the extent to which we have institutional knowledge about the types of economic problems that are unfolding at a point in time. We can use transfer learning, and we can also use low-dimensional dense representations of words or sentences using embeddings. Okay, so I'll go through some quick examples. As I mentioned, we're going to do some text feature extraction in the live coding session, so I won't really get into the details of the coding here in the interest of saving time. Okay, so with respect to sentiment analysis, very often we use dictionary-based methods in economics. The law firm McDonald Dictionary, for instance, which is based on 10K financial filings, identifies words that are positive and negative in that context. It counts them in the text, And then you typically compute something like a polarity score, which is the difference between the positivity and the negativity in terms of word frequency. Now, computing these simple features like dictionary-based sentiment or word counts is something that you can do in a few lines of code. So for instance, if we want the word counts, we can use scikit-learn to instantiate a count vectorizer. We define the number of words that we want to count. Then we just apply a fit transform to vectorizer, and we pass in a list of strings where each of those strings corresponds to a document like a speech or a newspaper article or something. And then we'll get from this a matrix where each of the columns corresponds to a word, and each of the rows corresponds to a document, and then we get the counts or the relative frequencies. And we can use PySentiment too for the popular law firm McDonald dictionary if we want to implement that. And since I'm covering that in the live coding session, I'll skip over that for now. Okay, with the economic policy uncertainty index, we have a lot of indications that it seems to have useful predictive value in a number of contexts in economics and finance. And we also have, since it's constructed using newspaper articles, even though it's something that was introduced recently, we're able to go far back in time to construct the EPU index, which also makes it valuable because then we can train models on longer time series. We can see that it rises after the Great Recession in 2008 and 2009. And with the political turbulence in recent years, we've also seen elevated levels of the EPU index. Now, if we want to say use words as our input, the words themselves, not counts or frequencies, and say a sequential model, then we have to decide how we want to represent those words. So we can use a one-hot encoded representation where we just have a number of sparse vectors, all of which are orthogonal to each other, and we encode a 1 in the position that corresponds to a specific word and 0 elsewhere in the vector. Or we can use low-dimensional dense embedding. So the one-hot encoded vector, if you have 1,000 words, you have to use a 1,000-dimensional vector. With embeddings, we can use 100-dimensional, 500-dimensional embeddings. And the embedding itself will give us continuous representation over different features. So if we look at the first element in the vector, it actually corresponds to some specific feature of a given word. And so vectors, co-locate in the embedding space depending on how they relate to each other. And we have pre-trained embeddings that we can use, so we can just take our words and map them to one of these embeddings, which already contains a lot of information on it. Entropy is another feature. So I use entropy in recent work with my co-authors to see how this would work in a topic model. Let's say you have a model and you select 5 topics, and the 5 topics that come out of it appear to be something like inflation, output, debt, investment, and housing. Now, for each of the documents in the corpus trained on, you can see topic proportions for each of those topics. Now, if our topic proportions are a uniform distribution over the topics, then we have maximum entropy. So we don't have a clear single topic that emerges from that document. Whereas if we have a degenerate distribution where all of the probability is placed on a single topic like inflation, then we have minimum entropy. And this looks like a very useful feature to use in a lot of contexts in economics and finance. Then we have this memory feature that we constructed, that I constructed with 2 co-authors earlier this year. So we take the new model by blind co-authors, the dynamic embedded topic model, which produces a time series of embeddings for each of the topics in the model. And then we take the embeddings and we compute the inner product for all pairs of years. And this gives us a measure of the strength of the association between the way in which a topic is described, say, today, and the way in which it was described in the 1970s. So for instance, if we have a development in financial markets today, and we have a financial topic, we can take the financial topic embedding, and we can compute the inner product with all past years and see which past years were described in roughly the same way as the events that are happening today. We can also do feature extraction with with BERT, so we can do things like hypothesis entailment to check whether a sentence or a paragraph is making a certain claim. We could do zero-shot classification with a set of predefined topics. We could do zero-shot sentiment analysis. These have been, I'd say, still fairly underexplored in economics and finance. We still have some ways to go to do a comparison with more common existing methods in economics, but this is something that could be done. Now, once we've extracted our features, then we can combine them with our tabular data. We could use them in a standalone sequential model, or we could say use a multi-input model that processes sequential text data in one input, and then in the other input takes in our tabular data and then produces a single prediction based on that. Now, on the live coding session, we'll focus specifically on doing feature extraction, and we'll compare a common dictionary-based method to the BERT model. Okay, so the last thing that I'm going to cover, and this will be mostly at a conceptual level, but again, we'll do an exercise in live coding session, is generative adversarial networks. Now, we have relatively few applications of this in economics, two that stand out. So the first is a paper by Susan Athey and co-authors that looks at using GANs to generate data that appears to have similar statistical properties to a given sample of data. So sometimes you have a very small sample of data and you need to bootstrap it, or you need to perform a Monte Carlo simulation that shows that if you have data with that property, then this will imply something. Now with GANs, we have an alternative means of generating data that looks like the data that we have in some very small sample. So it's an alternative way of designing Monte Carlo experiments. We can also estimate theoretical models using indirect inference with GANs. So this is an application for Kai and co-authors. And here, what we're doing is, we have a theoretical model, and it has parameters that we can't estimate directly. So it might have, the embeddings. It might have the preference parameter of an individual in the model. And that's not something we can measure directly. And so what we do is we simulate data from the model, and then we match some moments of that data with empirical moments. And we keep re-simulating until we find a model that matches the data well. And so GANs can facilitate that process. GANs can be used to do indirect inference. Now, how does a generative adversarial network actually work in practice? Well, I'll give an example with images. So with the generation of fake images, which is proven to be a fairly successful use of GANs. So essentially, we have two parts to our network. So we have a generator component and a discriminator component. And the generator component takes a latent vector, which is just a randomly generated noise vector as an input, and then it upsamples it to produce something that has the same, in this case, an image that has the same dimensions as the true images that we'll use in the training process for the discriminator. So to fix an example, let's say it's images of dogs. So we have true images of dogs that we've compiled, and then we have a generator which is trying to generate fake images of dogs. Now, initially, we feed noise into an untrained network, and we're just going to get noise as a result. We're not going to get anything that looks like a dog. Now, what the discriminator does, it takes the real dog images and the fake dog images, and it combines them to produce predictions, to classify whether something is really a true dog image or a fake dog. Now, the training process is iterative. So the generator wants to do a better job of tricking the discriminator, and the discriminator wants to do a better job of discerning which images are true dog images and which images are false dog images. So how do we know when the training process has converged? This is very different from training, just a standard neural network. Well, we use the concept of a stable evolutionary equilibrium. We want to find a point at which the discriminator can no longer get an advantage on the adversarial model, which is a combination of the adversarial model is how we train the generator. And the adversarial model or the generator isn't able to get an advantage over the discriminator. So they arrive at a stalemate where neither one can improve. That's typically where we terminate the training process. Now here's an example for the generation of simulated GDP series. So again, this is something you might need to do in a Monte Carlo experiment. The true GDP series is shown in red in the center. And then we use a two-dimensional latent vector for the GAN, and then we just vary the dimensions, those 2 dimensions of latent vector to generate slightly different GDP series within this grid. So all of the other GDP series are fake and are generated by varying the latent vector. Okay, so how do we generate GANs in TensorFlow? Well, we can use a mixture of TF-Keras and also native TensorFlow to simplify the construction of GANs. The trick is that we have to generate a discriminator object, a generator object. We also have to define an adversarial network, which is where the generator creates fake examples and then tries to trick the discriminator into misclassifying. Now, one of the difficulties that we can handle on TF-Keras is that we have to do weight sharing. So the adversarial network contains the discriminator network, and it has to share weights with the discriminator network, but we don't want the weights to be updated when the adversarial network is being trained, because otherwise the adversarial network will just make the discriminator do a bad job. So the weight sharing is one of the tricks that we need to figure out here. Now I'll move over to the live training session where we'll construct a GAN to simulate GDP.